Hello everyone and welcome to the Midas webinar. My name is Adam Kane. I'm going to be taking you through proceedings again today. Just want to do a brief sound check for about 10-20 seconds. We've run a test before, so can you raise your hand or place your comments in the comments box if you're in the room and you can hear me? That'd be great. Okay, that's fantastic. I'll just make a start. So this is a presentation for 3D geometry modelling and numerical analysis by finite elements for geo-structural problems. My name is Adam Kane. I'm a technical support engineer at Midas. Details are on the screen, so if you are having technical difficulties, then please phone the number or send in an email. Alright, so just going to give you a brief introduction to Midas. We do provide the complete software solution package in the form of buildings, bridges and geotechnics. Our geotechnics is all finite element and it's both in 3D and 2D. We can even do, and what we're going to be focused on today is Midas GTS NX, which is our latest release for the geotechnical software engineer. So just go briefly through the webinar content. You can see it on the screen there. I'm going to give you an introduction, go through a geotechnical analysis roadmap, so explain everything, and then go straight on to geometric modelling, constitutive modelling, finite element mesh, structural elements, where I'll take you into the modelling space, the interface elements, loads, boundary conditions, and the analysis controls. So just to give you an introduction. So the main objective of any geotechnical analysis is to determine and assess the forces, the stresses and also the displacements which develop in soil and structural elements such as walls and piles. A geotechnical engineer or designer also has to ascertain the movements in structure or in the structure and the adjacent soil. One particular case typical in London would be determining the heave in front of a retaining wall and depression behind the wall due to the wall's movements and the soil movements around it. So to obtain a solution for a geostructural problem, the following conditions have to be satisfied. So they're just listed on the screen. I will expand on the points a bit further. So the internal forces and stresses which develop inside the model domain should be a equilibrium or in equilibrium with the external applied loads. At any point during the analysis, the ground layers, elements and nodes should not overlap with each other, otherwise you won't be able to get a good connection between them. So in short, a physically impossible situation should not occur during the analysis or the modelling stage. Stress and strain increments developed in the soil and the results thus obtained should match with field measurements, so any kind of soil investigation for your models that are going to come back. If a physical situation can be idealized, then it can be solved as a plane strain or axisymmetry problem. However, if idealization for analysis is not possible, such as in the case of tunnel interconnections, then 3D analysis should be done. So as you see on the screen here, the complexity of the geometry where you've got tunnels going in several different directions and the soil strata is also curved in different places and of different levels, then 3D geometry has to be modelled and analysed. So just to give you an inkling into the analysis method. So here you can see the comparison of different analysis approaches on the basis of conditions which we just discussed in the previous slide. So for practical situations, limit, equilibrium, beam spring or full numerical approaches are used. Beam springs and numerical analysis methods are clearly advantageous over limit equilibrium, as the compatibility and boundary conditions for displacement equilibrium are satisfied automatically. So the modelling that you carry out can be satisfied automatically within the program. So the full numerical analysis, such as through finite elements or finite different methods, then has advantage over the additional beam spring approach, as a soil volume is not idealized as springs and you can you get the full soil structure interaction and deformations in soil, which can be calculated as well. So to conclude, for complex geometries you have to use 3D numerical analysis in the full numerical analysis. So this is the roadmap. So at the first level analysis, a designer has a focus on the problem geometry in hand, whether it is in a plane strain, axisymmetric or 3D analysis problem. Then you have data from site investigations, direct shear stress, triaxial test on soil, and have to keep the design requirements in mind. As you come down to the next level, you see the finite element mesh that needs to be created for the geometry or any complex geometry. As you go down to the next level, for the design requirements, you have the construction sequence, or the elements you have to input into the system. Then you've got on the other side, from the site investigation, the constitutive model that you're actually going to select. So you obviously just underneath you've got strength, stiffness, permeability. We're talking about the Mohr-Coulomb and things like that, and these are all entwined into the constitutive model. And then you merge the construction sequence with the constitutive model, and then you get the numerical solver, and then that is a prediction. And what you have to do is you either compare that against the reality in the form of anything from the site investigation or from existing papers in the field of a similar context. So if you go back to the reality check and that doesn't feed in with the construction sequence or the numerical solver and the prediction that you've had, then you go back to the constitutive sequence and the constitutive model, and you actually change the model you're using so it more suits the reality check. So just going through the geometry modelling, so it's a simplified version of actual field conditions. So if you are carrying it out, then you don't really want to overcomplicate things by adding parts of the model that are not existing, like extractor fans and things like that. You just want to add the model or the liner of the tunnel and the rock bolts, which are displayed in this geometry. For any interconnections and things like that, then it can become more complicated, but it's down to the designer to select what surfaces or what modelling he actually wants to carry out within the modelling space or within the 3D model that he's created within GTS or any other program. So just going on, so what a geometry model should represent, which is the ground layers, the topography surface if it's non-horizontal, and as you can see from the image here, then you can have any complex geometry, and there's different strata and there's different cuts coming out of that actual ground layers. You can model anything from the solids, the surfaces and the lines to model the ground and structural components such as solid volumes, walls, props and etc. for other construction stages. This meaning within GTS NX we can model pretty much anything effectively. So now we're just going to go over into the modelling space, and I'm just going to show you the model that we've generated. So first of all, you can see the graphic user interface is very enables you to move around very effectively with the ribbon technology. So you've got the geometry at the top there, and you can draw anything. Then you've got all the mesh that you can incorporate, going on to the static and slope stability with all the different forces, seepage and consolidation, dynamic analysis, and all the way through to analysis of results at the end. Here you can see the works tree where all your information is built up, and I just want to flick on the geometry and flick it back off again just to show you all the solid elements and everything. So you see the different materials that are created, and I can just quickly show you those. And you can also flick on the wireframe. So this is where we created our geometry function from, and cutting planes using the Boolean function and other things like that. As you can see, the tunnel entrance and the rock bolts. And here are the solid planes and the surfaces that cut through the actual solids that we generate to make up the whole solid object. So here is the complete solid with all the different material types and layers. You see we can set this to a wireframe, or we can set it to lines. So as you can see, all our construction stages for the tunnels there, and you can see the shadings and lines as well. So visually in GTS is absolutely outstanding. I'm just going to set a few layers to transparency just so you can look straight through the model. So as you can see, you can just visually look through the model there, and you can see the tunnels as well in the background and all the construction stages. So just to flick these off now and hide them. Oh, and one more. So as you see, there's the tunnels again. So as you can tell, it's very easy to move around the modelling space and to manipulate it in any way you see fit. So I'm just going to take you back into the presentation now and just go through the next couple of slides. So just talking about the constitutive model. The constitutive model relates to the incremental stress and the incremental strains, with a stiffness matrix representing the stiffness of soil and the structural elements. So the structural elements within the model, whether they be the beams or the shotcrete, anything like that. So it's expressed either in terms of the total stress or the effective stress or the pore stress of the soil or the water, well, effectively the water pressure. So the soil and rock behaviour can either be the linear elastic, the non-linear elastic, or the elastoplastic, creep, isotropic and anti-isotropic, and also the strength and the stiffness, which is modelled within the program. Permeability parameters, which are the soil water content curves for the unsaturated soil, which are all related to the constitutive models actually within the program. So just to take you through the little flow chart at the bottom, then like we discussed in the previous slides when we said that from the ground conditions or the soil investigation you have on site, which can get fed back to choose your constitutive model, and then you can carry out the analysis, carry it out with the verification or through the modelling space. Then obviously from the field measurements previously stated, we can check them against for the verification, or we can look at the back analysis, which are basically any papers that may have been published on similar models, which is previously mentioned. And if that doesn't all line up, then you go back to the start and pick a different constitutive model. So we're going to look at different constitutive models which are applicable to local ground conditions or local soil conditions. First one we're going to focus on is the anisotropic elasticity. So I'm just going to read through the slide and briefly explain what's happening in the diagram. So different elastic stiffness in the local orthogonal system. So that means that the actual coming down force, which I'll indicate with the mouse. So that's the force coming down from the side. Then you've got the soil layers, which are considered as transversely anisotropic, and which have different stiffnesses. So as you can see here, here's the different layers, and there's the direction of the disposition going down, and then you have the plane of the disposition as well. So these are the planes moving across, and there's the planes there. So there you've got the input parameters, which are the elastic moduli, the poise ratio, and also the shear moduli, which is indicated in G1 and G2. So we're next going to concentrate on the Tresca, which models the undrained behaviour as saturated soil, and the structural elements, i.e. the metals or any metals which make up the structure. The total stress analysis, and we also focus on the input parameters, which are the undrained stiffness, the undrained poise ratio, and the undrained shear strength, indicated as EU, VU, and K. And we look at the yield stresses for metals and CU, or phi equals 0 for solids, which are obtained from the UU test. Next we'll look at the modified Mohr-Coulomb method, or constitutive model. So this is suitable for modelling normally consolidated soils, and soil behaviour considered, the soil behaviour considered are the pressure dependent shear strength, the compactions taken into consideration, and the non-linear elastic unloading. The double hardening model, or the Mohr-Coulomb shear yield surface, and elliptical shapes compression yield surface as well. And we also focus on the input parameters, which are the secant stiffness, the ediometric, the loading and unloading, the delayancy angle, and the friction angle, and the reference pressure. So now we look at the modified cam clay layer, which is applicable mainly for the London area. So focus on the isotropic, elastoplastic, the hardening model based on the critical state concept, which is suitable for modelling normally consolidated or over consolidated clays. The parameters based around the field tests that are carried out. So the lab tests that are generally carried out in practice. So next we're just going to focus on the jointed rock. Within this constitutive model, the anisotropic, elastic, perfectly plastic model, the shear strength at anisotropic joints interface given by given by Mohr-Coulomb failure criteria to simulate the behaviour of joints and the stratified rock layers. And so the input parameters are similar to the transversely isotropic model, with the addition of a cohesion, a friction angle, and a deep angle. So now we're going to go back into the modelling space and show you some of the constitutive models. So we're just going to go up and look at some of the materials, and just look it up and show you the different models that there are. So I just want to modify one of these. So this is the modified Mohr-Coulomb. We can also look at the different model types, so you can see them all there. And Tresca, and we could just select the different porous and nonlinear attributes of the soil itself and the model. So just want to highlight that you can actually export to an Excel file for easy checking of the model itself, and you can also import from Excel if you created your own, just to make it more flexible for the user. That's my fault. So now I'm going to take you back into the modelling, back into the presentation. Sorry, we're in the modelling space. So just continue on to the next point. So we're just going to look at the finite element mesh. So the geometry is divided by finite elements, and the summation of behaviour of individual finite elements represents behaviour of the global system. So the types of finite elements are continuum or volumes, asymmetric, plane stress, plane strain, shell, beam, truss, and interface elements. In any mesh, elements at common locations must have shared nodes. So this is between, say, two solid elements, I suppose. The displacements, rotations are calculated only at nodes of the element. Within an element, results are obtained from interpolation. The order of interpolation is described in the two diagrams below. So the order of the elements is either one linear or two quadratic. So in order to find the actual forces within the centre of the element, then it's done by interpolation in a linear order, as you can see in the first diagram, or in the second order where the actual elements split up by the nodal points in which are dividing the actual element itself. So just define the different finite element mesh. As you see here, you have two types of mesh, which you've got the auto mesh function that we can generate within the program, which will give you an orderly mesh, but it won't be as orderly as a map mesh. A map mesh can be used really on just where you take a surface and you can extrude it, but if you've got a more complicated tunnel intersect like in the first one, a more complicated geometry, i.e. the stratigraphy of the ground layers are more diverse and complicated, then you'd have to use the auto mesh function. This is for more accurate prediction of the results in the 3D analysis, where we use the hexahedral element dominated mesh. As you see here, you've got the linear heterohedral and you've got the linear tetrahedral. So I said the heteral wrong there. So heter dominated mesh, as you can see here in this model, where it's more of an orderly fashion, and you can see the combination where it meshes at different points. So moving on slightly for more about the finite element mesh. The mesh density, the density distribution of finite elements is in a domain where you can control it, where a finite mesh size at areas of stress concentrations and localized deformations areas are under, for example, under a strip footing. Controlling the mesh density is used by using seeds for the manual definition of appropriate mesh size. You've got different types, element size, divisions, linear grading, and the hyperbolic distribution, which can also affect the seeds. And then you've got the level of fineness and coarseness in the mesh generation. So as you can see from the diagram at the bottom, you can control and refine it to what you wish. So the mesh quality parameters, which is you can see in the linear grading, the seeds which are generated along the edge, and as those seeds get finer, as you go to a more concentrated mesh where the tunnel is, then it actually seeds to that point and becomes more dense and finer. So now we're going to go back in and I'm just going to show you the mesh in the actual program. So I just want to flick all the layers back on. Go to hide all, then flick all the mesh on. So as you can see, we've got meshes to be generated for all the different surfaces and everything. So we can select different colours for this and manipulate it. And we can also look at managing the material colours. So as you can see, they've changed in the actual change of the mesh. So these represent the colour of the materials that's been assigned to them. Just look at the different mesh sets. So we just want to select some of these and hide them. So I just want to select all of them and just show you the tunnels. So you see the tunnels with the different construction stages as well. So let's look at the front. As you can see, you've got the tunnels been separated into all these different segments. And you see the rock bolts and everything. And these are all the different construction stages going throughout. And you can see the shotcrete. And the zone for grouting as well. So we're just going to go over to the structural part now in the PowerPoint presentation. So just concentrate on the structural elements. But the structural elements such as nails, anchors, props, whalers, solid soldier piles, board and driven piles, CFA, panel walls and other structural elements can be easily modelled within FEA or an FEA type package or GTS NX. Finite element types, beam, truss, springs, shells and solids, where you can take the forces and the bending moment results into account within the program. Common problems are unconnected nodes between structural meshes and ground mesh at common locations in other programs, but in GTS NX connections are automatically guaranteed using two methods. Either the imprint method, which is the shared connectivity between an edge and a solid plane, which you can see here. You can see the actual element and then you can see the actual solid plane. Or the column connected to the slab there. You can extract elements by creating a mesh for structural elements from the shape of a ground mesh as well. So as you can see the solid there, and you can actually manipulate one of the sides and extract it and create a 2D shell element which is extracted from that 3D mesh. So we're just going to look at the interface of elements. So the interface of elements are used for full solid structure interaction, which allow the slip between the structure and the soil at the common boundary between the two elements, or between the structure and the soil. The mesh level, the interface elements can be defined automatically along the line elements such as beam or truss, or the plane elements. So the plate, or the curved plate and the soil, and the interaction between all of those different things. So there's no need to model actual thickness of elements, which prevents the spurious results due to thin volumetric elements. The input for reduction factors of strength for auto calculation of the interface, where the strength and the stiffness are a factor, where the factors are usually in the range of 0.5 to 0.7. The choice of value depends on the type of soil and the structure that is being modelled. So for the action between say a clay and concrete and a clay and steel are going to be different. and as you can see that this is from the line and the plane type of interface element in the diagrams at the bottom there. So now to just take you into the model and show you some of the different elements. So it's going to bring over the modelling space. Hang on. So we're just going to look at a different model, so just a basement construction here. So just look at some of the different meshes. I just want to turn some of them off. You don't need them, so we're just going to hide them, and these are the structural elements that have just been highlighted. You see those are the actual, these are the levels, and then you've got the columns and the interaction. I'm just going to show the interaction between the two. So this is a column here, and you see the nodal connectivity between that and the planar element underneath. So just to show you the nodes there. And just select the node, so as you see that nodal connectivity. We just want to look at some of the properties of the struts and the walls. So as you can see there, the I section is being used for the strut, or the column, sorry. So just looking at some of the actual elements and the sections, and also some of the values for the I section there, so you can see, and you can change it, so you can change it to box, or you can change it to any angle or anything like that. So we've got all the elements built into the program and the actual material properties. So just look at some of the properties and some of the elements, so we can modify some of these or create them. So we just want to quickly modify one of the wall elements, and this is the structural material, so we can change the values for the thickness and also so just to clarify that the model the full structure soil interaction and the nodal connectivity between the elements and the soil layers. So I'm just going to take you back into the PowerPoint presentation just to go through the loads. So as you see, a comprehensive list of loads from self-weight, the forces, moments, prescribed displacements, pressure and water pressure, all the way through to the dynamic seismic load data generator, response spectrum analysis, time history analysis, and the time forcing function as well, including 54 different earthquakes. So here you can see the pressure on a surface and also the pressure on elements. So it doesn't matter if it's a planar element or a mesh surface, we can still attribute the loads to it, and we can transfer the loads from the standard loading over to the finite elements. So just a few boundary conditions, so some simple ones in the form of supports. We've got the constraint equation, nodal flux and surface flux, which are your water conditions, and seepage face. We can also look at the slip surface or the circular polygonal, and we can look at the unsaturated property function in the form of suction and heave. We can look at the consolidation and the draining conditions as well. So we can even look at the change of properties with construction stages. So just go through some of the analysis control. We've got the solvers. So we've got a 64-bit integrated solver, and we've got multiple processors to accelerate or make the analysis faster. For the different solver types, we've got a multifunctional, dense, AMG and eigenvalue. But we can also we've got different element formulations in the form of hybrid, reduced and standard, and the soil behavior, which is K-naught analysis, and we've got partial saturated soil and the limit negative pore pressures. For the nonlinear stiffness update, we have secant and tangent. And for incremental procedures, we've got different incremental procedures for the smooth convergence, fast analysis and accuracy of results. So I'm just going to go over to the modelling space. I've got 3 different models to show you. So I'm just going to focus on the first model. I'm going to show you some of the ground conditions. So just going to turn everything back on there and just show you some of the ground supports. So there's all the ground supports around the outside. You see the tunnel going through the bottom there. So just going to show you some of the mesh sets now, just quickly. So we're just going to select a number of them. So just to show them. So as you see, this is the grout layer or the shotcrete layer at the outside of the walls through the different construction stages. So you see there's the grouting zones, which is a change of material properties which form from foam concrete, from ground to concrete. So they were ground layers and now they're concrete layers. So just going to look at some of the load cases in a minute as well. So I'm just trying to find something. Right, there we go. And those are the floor layers going up through. And we also got the pressure loads on each individual floor that we can simulate in the model. And we can edit those as well and manipulate them and change the values depending on how many kilonewtons you want to put on there, and it will carry out the analysis depending on the material type. So just to flick on all the meshes again and take you back. So there you can see all the loads, and we're just going to take you into model 2 and show you some of the blast vibration analysis. So this is obviously key for existing structures, and any blasting is going to be carried out. So as you can see, there's an excavation, there's an existing building, and there's an excavation where we're going to carry out the blasting. So first of all, we're going to look at the time varying force function, which is applied to the blast hole. So as you can see that I've highlighted it, and we can also edit the time forcing function, and you can manipulate that and change it so that you can see the wave or the blast is going to be carried out. So just to show that we can edit that as well. And so this is a time varying pressure load. I just wanted to show you that there so you can actually visually see it. And the arrows represent where the load is being applied and the force. And just go on to the consolidation model as well. So you can apply the pore pressure conditions to the model water level for consolidation. So I just want to show you those. Let's see the actual nodes there and the connectivity, and that's the pore water pressure. And we can look at the influence of drains as well. So the drainage conditions, as you see, there's the drainage conditions, and the nodal head as well, the flux. So excess pore pressures for drains are modelled with the zero head. So as you see there on the screen. Okay. So for the embankment, which is made out of sand, we can control the consolidation. This consolidation doesn't happen in sand, so we can apply a boundary condition for this in effect. Now we're going to show some of the results in the post-processing for the first model, so we're just going to go back to the basement construction. So just to look at some of the post-processing, so just go into post-processing and look at the results now. And look at the solid stresses, so we can look at them in any direction. So there you go, that's the solid stresses in the ZZ. And we can look at it through the different construction stages as well, as you can visually see there. And it gives you all the cutting diagrams and everything. So excavation 3, which is the bottom of the pit, we can look at the construction stages here. And the deformations and stresses. And we can look at the cutting diagram as well to the side there. So So we can also look at the structural elements and the stresses, strains and everything like that on them as well. So just to highlight them, just to make sure we can just visually see them. Oh, just go back, just want to find the other structural elements as well. Flick them on. Just want to look at the results, so just got to go into results so we can't see anything on the screen. So just want to look at the total stresses, yep. So here we can see the displacements. We can also look at the shell element forces as well. We just want to look at them in the YY direction. And we can also look at the transverse shear forces. And we can even look at the actual forces as well for the elements. So as you can see there, there's the actual forces. And the bending moments as well. And obviously you've got a nice key down the side to tell you where it's all maximised. Just back to the mesh. So let's look at the solid stresses as well, going all the way through, so we can visually see it for the shell plate and the solid, and we can even set the shading so it's different and manipulate it. Just want to carry out a bit of tagging and some probe results. So as you see, you can just tag any area and you can actually do a probe result effectively just to find the stresses or the maximum strains, and you can do that through the construction stages as well. Okay, that's it. So I just want to take you back to the presentation. Just to close. So that was some of the results features you can see in the GUI there. So I just want to go on to the last slide. So let's go to the last slide. So thank you for coming to this webinar once again. I hope you've learned a thing or two in geotechnics and enjoyed the presentation. You can find all of our content on YouTube for additional learning, and you can even just give us a call or give us an email and we'll come along to your office and give you a bespoke presentation and demonstration of the software. So by all means, please do come back to us and we'll assist you. My name's been Adam Kane, and I'd like to say thank you and goodbye.